Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on September 28, 2025, which was about 12 days ago. The striking result is that this paper introduces MemMamba, which keeps linear efficiency yet resists long-range forgetting, maintaining perplexity 17.35 at 60,000 tokens, preserving about 90% retrieval at 400,000 tokens, and delivering a 48% inference speedup. The paper is titled MemMamba, Rethinking Memory Patterns in State Space Model. And as we'll see later, the gains show up both in accuracy and in speed. Beyond the results, this paper explains why Mamba forgets, and proposes fidelity metrics that track memory loss within tokens and across layers. So Figure 2 explains how a MemMamba block layer keeps long-range context while staying efficient. The left panel shows tokens flowing through a note block that writes compact summaries into a bounded state pool, which acts like a small notebook for salient facts. The right panel details retrieval, where cross-token attention queries that pool to restore forgotten content. A state space model update then integrates the retrieved signal, which is a recurrent rule that advances a hidden state over time. Periodic cross-layer attention aggregates summaries from prior layers so information does not fade with depth. Alright, Figure 1 presents the overall workflow, which illustrates how stacked MemMamba layers keep salient context while enabling long-range interaction. The diagram shows inputs passing through MemMamba block layers that write compact notes and then route updated states forward, so critical clues persist even as depth grows. The note block is a tiny summary store that captures only the most important tokens. Cross-layer connections provide periodic shortcuts that refresh memory without quadratic cost. Well, Table 1 compares perplexity across context lengths and models, which means how surprised a language model is on average, so lower is better. The MemMamba row shows stable perplexity around 17 at 60,000 tokens, indicating strong long-range memory. Mamba's perplexity jumps above 30 by 20,000 tokens, signaling severe forgetting. Mamba degrades further, exceeding 40 by 40,000 tokens. So, Table 2 reports passkey retrieval accuracy across context lengths, meaning whether a model recalls a hidden key token in very long inputs. MemMamba sustains perfect accuracy through 256,000 tokens. At 400,000 tokens, it still scores about 90%. Mamba 130M collapses to 0 beyond 32,000, which signals severe long-range forgetting. Mamba 130M stays perfect up to 256,000. At 400,000 tokens, Mamba 130M falls to about 60%. So, Table 2 covered retrieval. Figure 4 shows memory fidelity trends across Mamba variants. The left panel plots effective token memory fidelity, which measures how well a model preserves earlier token meaning. The green line stays near 0.45 across lengths, while the orange and blue lines remain much lower. The right panel shows effective cross-layer memory fidelity, which tracks information passed through depth. Mamba rises with length toward about 0.45, but is reported unstable. The green line from MemMamba holds steady near 0.26, and coupled with strong token fidelity, overall memory stays reliable. Alright, Figure 3 presents an ablation that tests which mechanisms matter, meaning an ablation study removes or adds components to measure their impact. The left panel tracks perplexity across long contexts, and it stays near 17 for MemMamba, while Mamba spikes sharply as length grows. The right panel compares inference time and shows roughly a 48% speedup over a transformer, with Mamba similar. These results indicate stable memory and strong efficiency. Wrapping up, two takeaways stand out. MemMamba counters exponential forgetting by pairing compact note summaries with sparse cross-token and cross-layer attention, and it keeps linear efficiency while sustaining strong long-range accuracy. The new memory fidelity metrics make degradation measurable, which guides future ultra-long context design and deployment. Thanks for listening. I am Alex.